the next part of 2.6 is getting you to recognize which ones can be 0. So we have this, we already talked about possible positive, possible negative, and we're slowly getting to the imaginary part. But if I were to ask you to factor all of this, I would start with the greatest common factor, and you'd left with x squared plus x minus 2. So you still have that x in front. So what you now have is x plus 2, x minus 1, and you could confirm then that you have a 0 at 0 from this, a 0 at negative 2 from this, and a 0 at 1. Perfect. So then looking at the next one, just trying to change colors up again, you can factor out an x squared, greatest common factor, x minus 3. Well, what you notice then is x equals 0 right here has a multiplicity of 2. And that's confirmed in the graph. It just bounces off the graph, and then x equals 3 crosses right there. And one more. Now this one, as we notice, you'd have to factor by grouping. So you'd have an x squared to pull out in front, x plus 1. You can pull out a negative 4 there, and you're left with x plus 1. So then you can combine your x squared minus 4 because the other parentheses is exactly the same, and then you have a difference of squares, x plus 2, x minus 2, and x minus 1, and all of those are confirmed at negative 2, negative 1, and 2. So what they're trying to get you to notice, and I'm going to leave the screen right here, is how many zeros, what's the multiplicity of x equals 0 as a root? And how can you tell by looking at the graph, and then how can you tell by looking at the equations up here, f, g, and h? So this one definitely has a 0 one time. And as you look at this, there's a clue in the part that you could factor out an x because it was shared in all those terms. What I'm boiling it down to is that there was no constant here, or if you write a constant, it would be plus 0. Now, how can you tell by the graph? Is it crosses? This one crosses, and there's no point of inflection, no change in concavity there. Now, as we look at the next one, it's a root 2 times. And this is because it bounces or just touches. I don't know what phrase you want to use. I've been using bounces lately. But how could we tell by looking up here? Okay, well, there's still no constant, but as you notice, our greatest common factor was x squared in that problem. So maybe that's what we need to be highlighting. Here's a highlighter. We should be highlighting that there's no constant and the greatest common factor that can be pulled in front. Because on this one, it was 0 times, and there was a constant. And why am I pointing out the constant? Is that's how it shifted down the graph. So if it shifted down the graph, it didn't cross at the origin. Did not go through the origin. I hope all of this is making sense. It makes sense to me, that's why I say it. And the main difference that we're looking for is 2 of them did not have a constant. Is the constant. No constant versus the other one had a constant. And the reason why that's important is having a constant shifts the graph up and down, whereas not having a constant means it has to pass through the origin. Origin versus a different y-intercept. Maybe that makes more sense to you. So based on this, how will you determine the number of times that x equals 0 just by looking at the equation is by looking at where the constant is. So this one has a constant there, and what the greatest common factor would be. So the greatest common factor determines the multiplicity. So if it has a constant, like this one has, a constant is present, constant is there, that implies that there are no roots at 0. Now, what if this wasn't here? All right, so I'm just going to highlight as I go. If that 3 was not there, there would be a root at 0, and it would be the exponent of this 1. So there would be a 0, the multiplicity would be 1, because that's the greatest common factor. Well, what if the 2x and the 3 were not there? Well, now there would be a 0, and its multiplicity would be 2, because that's the highest exponent, the greatest common factor. So let's remove that one. What if that wasn't there, as well as the 2x and the 3? Well, now it would be a multiplicity of 3, the highest exponent here. And then what if that wasn't here? Well, then it would be a multiplicity of 4, but I will not give you a problem like that. So hopefully that quick story time helped you realize what I'm looking for. So basically what it boils down to is everything else must be imaginary. So the thing about imaginary, though, is they happen in pairs. They happen in pairs. And that's part of the reason, too, why we have to break things down. So if you remember the quadratic formula, that's what this whole thing is. We're looking at a quadratic. And here's even the graph of the quadratic. Well, does it cross the x-axis? No. So that means there's no real roots. And if you did the quadratic formula, let me write that down. B plus or minus the square root of b squared minus 4ac. I hope you memorized this last year, over 2a. You might even use it this year. Notice that under the square root is what is called the discriminant. I'm probably spelling this wrong. It's the beauty of being a math teacher. You don't have to spell things correctly. It's called the discriminant because that's your indicator as to whether or not your answer has imaginary roots. Because if you square root a negative number, then, well, square rooting a negative is your indicator that you have an imaginary root. So if I went back to this problem, and I hope you remember that a equals 1 in this problem, b equals 2, right there, and then c equals 2. So b squared is 2 squared minus 4 times 1a times c, 2. Well, that's 4 minus 8, which equals negative 4. That's my indicator because we would be square rooting the negative. Well, the square root of negative 4 is 2i. The square root, oh, that does not look like an I. I always put a hook on my eyes. That's traditionally what we do in math. The square root of 4 is 2, and the square root of a negative puts the I there. So that tells me that it does not cross the x-axis, and we have, sorry, I forgot to write, plus or minus. So there are 2 imaginary roots. They happen in pairs. Well, if we finish the problem, and we actually figured out all those roots, plus or minus 2i. Man, I'm terrible at writing i's today. 2i all over 2 times 1 is 2. We would just make sure that you distribute that, dividing by 2 to each term. Negative 1 plus or minus I. So they kind of explain everything. Since imaginary roots come from taking the square root of negatives in the quadratic formula, what are the possible number of imaginary roots for a polynomial? Well, they either never happen, they happen as plus or minus, or if there's two sets of them, there could be 4, and I won't get up to a polynomial of 6 terms, but it would be 6, 8, 10 possible imaginary roots. I hope all of that makes sense. So this is the same problem we looked at before. And so what all I need you to realize is that because that it's a fourth degree polynomial, we could have all four of the roots be imaginary. Or if it happens in pairs, they could have 2, or they could have 0, and possible imaginary. Sort of the same explanation as we had up there. So what we'll be doing is, I actually don't like how they write it out like this, is I like to write a table. And you'll actually see a table in the homework where you'll see it written as a, hold on, as positive, negative, I like to just write 0 here, or imaginary. And I don't know, it's just my pen, I guess. I'm struggling to write I's. And then what we can do is we can put down all of the scenarios down. Because if you recall from the possible number, this is the same problem from the first video, that it was 2 or 0 for positive, 2 or 0 for negative. Well, we didn't do this one yet, but what was our clue? There's a constant, so there's never going to be a 0 root. And then this one was 4, 2, or 0. So you have to make a table that lays all of those options out. Because we could have 2 positive, 2 negative. Well then, because it's a fourth degree polynomial, there's none left over to be imaginary. But it doesn't have to be like that. You could have had 2 positive, 0 negative. This one's always going to be 0, as I said. So there would be 2 imaginary. Remember, the sum has to add up to be 4. Let's do another one. I think we've exhausted the 2 positives. But we could have had 2 negative. This would still be 0. And then 2 imaginary. And there's one more scenario, I don't know if you've thought about it, where none of them cross the x-axis. None to the right of 0, none to the left of 0. This is still 0. But all 4 of them could have been imaginary. So instead of rushing through the next page, I'm going to stop here and take my time for a third video.